Good morning. Welcome, everybody. We're happy to have with us today Hadley Wickham from Rice University to talk to us about engineering data analysis with R. So with that, I'll just hand it over to Hadley.
Thanks, Ryan. So today I kind of want to talk about one of my sort of current interests, which is data analysis. So what do we do when we kind of get data in and then we're trying to turn it into understanding or knowledge or insight? And I think we want to be kind of a little bit like engineers or scientists when we do this. We're not artists, we're not craftsmen. We really want to have a reproducible process which helps us go from our raw data to what we really want, some understanding. So I'll talk a little bit about what data analysis is, and then hopefully the majority of you are already convinced that you should be using a programming language to do data analysis. Are there any Excel users here, or SAS users, or anyone willing to admit that? Okay. So we'll talk about why you should be using a programming language, a little bit about why you should be using R specifically, and then I want to talk about a few of the things that I've worked on specifically in R, so some domain-specific languages for visualization and transformation. And then I want to show those off on a little case study of an interesting data set that I've been working with lately, looking at mortality in Mexico. Okay, so to me, data analysis is the process. So data comes on one side, on the other side we get insights, understanding, and knowledge. And that, to me, kind of, I identify myself as a statistician or a data analyst, and to me that's what we're trying to do. So all of our tools need to be towards that aim. We want to get raw data in, and we want to get understanding out. So whatever we do when we're working tools, we want to keep thinking about that. So I'm sort of struggling to understand or come up with a process which describes what we do in data analysis. This is my first attempt. So if you're going to do a data analysis, well, the first thing you've got to do is get some data. So the first step is to access the data. So sometimes that's easy. You're just pulling it out of a big database. Sometimes, particularly if you're a scientist, that's really hard. You've got to design some experiments, collect some data. But you can't do data analysis without data. Then what you're going to do is try and understand that data, and I kind of think about that as an iterative cycle of 3 sets of tools. So you're going to transform or rearrange your data, you're going to visualize it, and you're going to model it. So each of these components have particular strengths and weaknesses, right? Visualization is great for revealing the unexpected, but it doesn't scale very well. You've got to look at everything. So if you've got 100,000 variables, then looking at every scatter plot just isn't going to work. So that's where models comes in. Models kind of give you a nice scalable approach to data analysis. They allow you to basically pass off a lot of the hard work out of your head to a computer. Computers are cheap. We can have lots of them. We can do lots of stuff with models. But the problem is, at a fairly fundamental level, models won't tell you what you won't expect. So unless your models, because they are so specific, because they can scale so rapidly, typically they're not going to show you something that you just had no idea could be possible. Okay, so you're going to cycle through those things. Your visualizations are going to help you understand what you didn't expect. You'll capture that with models, loop through that again. Typically, as you remove the bigger structure, you'll find finer, smaller and smaller details that are progressively less and less interesting. So at some point you decide you've stopped, you've done the data analysis, and then the next step is to communicate your results to others. So you can kind of think of this understanding process as building up an internal mental model of what's going on in the data, and then the next step is to help others gain that same mental model, but with hopefully not quite as much heartache and hard effort as it took you to get to it. And then typically the cycle is going to lead around. Once you've communicated your results to someone else, they're going to want you to do some more. So you're going to have to collect some data, new data, or we can think about it similarly. You start with a question, you get the answer, and then those answers are going to lead to more questions. So if you're going to try and do data analysis, why do you want to do it in the context of a programming language? And in my mind, there's sort of 4 major advantages. So the first advantage is reproducibility. So particularly if we're being scientists, we want to ensure that everything we do can be reproduced in the future. I really like this idea of provenance from art. When you get a visualization or results of analysis, you really want to be able to track that back to exactly follow every step backwards from the raw data. So you can say, how did I go from the raw data to this result? And that tends to be really easy in a programming language, right? Because all you have to do is follow the code that transforms the data to your final visualization. And the flip side of reproducibility is automation. So reproducibility is making sure you can recreate the past and the present, and automation is preparing for the future in the present. So typically, you're not just going to get one static copy of the data. The data is going to change. You're going to need to redo your analysis, make sure you can update your conclusions as new data comes in. So for you guys, that's probably your data. You're constantly collecting data. Even if you're working in situations where you think there's one experiment, people collect the data, and it's your job as a statistician to help them analyze it. It's really been my experience. You meet with them, you get the data, and you say, "Is this your final data?" And they say, "Yes." And then a week later, they say, "Oh, hey, I just discovered this other logbook on the bottom of the filing cabinet. There's actually a whole lot of other data that I forgot to give you. Here's a new version." And then you do a little bit of looking at the data and discover there's some really weird things going on, and you talk to them about it, and they say, "Oh, yeah, that's right, I forgot about that. I'm going to have to give you yet another version." So if in the course of an analysis you only need, get 3 or 4 versions of a data set, I think you're doing pretty well. So, trying to automate these kind of tasks in a GUI like Excel, it's just a nightmare. You really, when you get a new data set, you need to be able to rerun your analysis very, very easily. So another kind of often overlooked advantage, I think, of a programming language is that it's just text. So this is some real big advantages because we've got a lot of great tools for dealing with text. So, if we want to see how our analysis is changing over time, we can use source code control. If we want to store our code for the really long term, we can print it out. If we want to reuse our code in some way, we can just copy and paste it. Right, and it leads to another really important aspect, I think, of code, which it also really supports communication. So if you've got a problem with code, you can easily copy and paste that chunk of code. You can make a little reproducible example, and you can stick it in an email. If you compare that to trying to diagnose what's gone wrong in an Excel spreadsheet, your process in an Excel spreadsheet, that's really, really difficult. In a GUI, it's pretty much impossible to capture what you're doing in any other way except by making a video. And, that's painful to do yourself. It takes a lot more setup than just copying and pasting some code. And it's also much harder for people on the other end to verify what's going on. So one thing that kind of surprised me, I used to teach a data analysis class where we had components in both Excel and R, and surprisingly, the students actually preferred R because they could see absolutely everything I was doing. In Excel, it's very difficult when you're showing someone something on a big screen. It's very difficult to distinguish, am I left-clicking or right-clicking? And just the tiniest difference, like, a pixel or 2 difference, can make a big difference in what action actually goes on. So another real big benefit of using a programming language is that it's so easy to communicate what you've done to others. The disadvantage of a programming language, of course, is that there's a pretty big learning curve associated with it. So pretty much everything I'm going to talk about today, I'm not aiming at kind of casual users of data analysis. If you're just doing a data analysis once a month or a couple of times a year, none of what I'm going to talk about really applies to you. Right, the people I'm interested in are people who are doing data analysis every day, where it's really worthwhile to make this investment to understand deeply a programming language so you do get these advantages of reproducibility, automation, the fact it's just text, and that it's easy to communicate. So if you've decided you're going to use a programming language, or probably you're already convinced before, hopefully you're already convinced before I told you, but these are the sort of the reasons that I think are the most important. Well, why should you bother learning R? So it's open source, of course. I think that's a pretty good start these days for any kind of data analysis platform. Again, connected to this idea of reproducibility, that anyone can reproduce it. They don't need to spend $10,000 or $50,000 buying the software just so they can rerun your analysis. Connected to that, R has a really strong community, so even if R doesn't have what you need now, maybe in a few years it will. There's a fantastic variety of add-on packages. I keep losing count, but I think there's over 3,000 add-on packages for R, which give you pretty much anything you can imagine in terms of statistics or machine learning. The downside of the community is sometimes it can be a little bit prickly. Our help, the mailing list for R, is a fantastic resource, but if you ask a stupid question, you can pretty much guarantee that someone is going to tell you that you're an idiot, either politely or not so politely. So in fact, I've been told on our help twice that I need to look up words in the dictionary. Both times I was correct, but... Another big advantage of R, it runs anywhere, Windows, Linux, Mac. People run it on their PlayStations and the Xboxes and so on. Pretty handy. And this idea, because it is open source, because you can add on to it, it's really build it yourself. So even if R doesn't have what you want, it's a real programming language, you can build on whatever you need. And again, so many other people have built on other packages that even if it isn't there in base R, and well, the chances are it isn't in base R, you can download a package. So sort of an interesting corollary of this is it's almost a disadvantage. So at the moment I'm working with a student reviewing density estimation in R. So there's about 25 different packages in R that do some kind of density estimation. So now R is getting to the point where if you want to try some statistical methodology, it's not does R have it, but which of the 10 different options should you use. So on the downside, R has a reputation as being slow, and I think compared to a lot of other languages, it is slow. But then typically we're not really interested in absolutes. Is this programming language slow or fast? What we really care about is it fast enough for what we need. And the big advantage of R is that it really is fantastic connecting to other programming languages. So while in some sense the R language itself is pretty slow, R is not, because so much of the high-performance computing stuff in base R is written in C and Fortran. And so this is a really big advantage of R. It's trivial to connect to C or Fortran. It's pretty easy to connect to Java. People have written connections to Ruby and Python and OCaml and all sorts of other things. You can read in data from just about any format imaginable, connect to all sorts of databases. The other the last downside I want to talk about for R is that to me, it's still sort of lacking some programming infrastructure. So the focus of R really has been on statistics and data analysis, and that's what people who contribute to the R community tend to be good at. By and large, they're people who want to understand their data. They're not programmers. And there still isn't an R sort of a culture like in many other languages of how do you do things the best possible way? How do we develop programming best practices? And I've kind of found this fairly frustrating myself that I've sort of had to build a whole lot of infrastructure myself. There's sort of not any very good unit testing packages in R. There's not good packages for understanding your profiling data. There's not some of the documentation stuff has only come to the scene relatively early. So one of the things that I've kind of spent a lot of my time doing, not so much because I'm interested in it, but because I want to be able to develop good R code, is develop a lot of this infrastructure. And so for the course I'm teaching later in the week is one example of this. So how can we help kind of people become R programmers? And I'm really hopeful as more people who have, more programmers, more people experience in other programming languages, as they come to R, they don't say, oh, hey, R is missing feature X, it sucks. What I want them to say is, hey, R is missing feature X. This is an opportunity where I can really contribute to the community and make a big difference. And I think there's still a huge number of possibilities for that sort of contribution in R. Okay, so those are the kind of the pluses and minuses for R. I mean, I haven't really compared it specifically to any other languages, but I think at the moment, at least for sort of, so it's a little bit hard to talk about big data versus small data. So as the sort of statistician in me thinks, 50,000 observations is a big data set, but the computer scientist in me rejects that as being big. So R, I think, is in a sweet spot for analyzing data up to about 1 million observations. And I think even if your data is bigger than that, the limitations aren't really on R so much once you get data once your data gets bigger, but the sort of the cognitive limitations. I think it's possible to work with about 1 million observations interactively, kind of understand what's going on there, and then in some way scale up. So think about how you're going to scale up your models or so on. So you never, even though and those 1 million data points, might represent 10 billion original observations that have been aggregated in some way. The trick is figuring out how do you do that aggregation and how do you make sure that when the aggregation is no longer appropriate that you still detect that problem. But what I want to talk about next is sort of within our, how can we develop domain-specific languages for specific tasks of data analysis. So some people describe R as a DSL for statistics, which I think is wrong. R isn't a domain-specific language. It is a general-purpose programming language. I mean, it has traditionally been applied, by and large, in the fields of statistics and data analysis, but there's nothing really built into the language at a fundamental level that implies that. So on top of R, we really do need to develop these DSLs that help us kind of automate and understand and think about the common problems we have when during a data analysis. And to provide a little bit more motivation for why we need to do this, here's a sentence from Euclid. So if any number of magnitudes are each the same multiple of the same number of other magnitudes, then the sum is that multiple of the sum. So can anyone tell me what kind of simple mathematical principle, algebraic principle he's describing? Yeah?
He's talking about multiplying exponents, which exponent adds.
I think, yeah, you're pretty close, but slightly simpler than that. So it's just this idea of that multiplication distributes over addition. Right, so here, what he's been doing is trying to express this idea, well, not in English, but in Greek, obviously. It's pretty clumsy, right? So we really have a domain-specific language, which is math, basically, right? So it makes it much, much easier, I think, to reason and to understand what's going on with this domain-specific language than it is when we're just trying to use natural languages. So the same thing kind of happens when we're doing a data analysis. What we want to do is make sure we've got domain-specific languages for each of these 3 components. That's going to make it easier for us to think about the problems. So, there's a component of any problem is how do you actually represent it on the computer, but there's a big problem, first of all, just how do you understand what you're trying to do? And I think domain-specific languages are really helpful there because they sort of help you understand, well, what are the key components of this type of problem? How can I break it out? How can I take these general ideas and apply them to my specific problem? So I want to talk about each of these just briefly, and then I'll show them off in a case study in a little bit more detail. So the modeling kind of domain-specific language in R is this sort of formula interface. How many of you guys have seen this before? Okay, so basically we're saying, in this one we want to predict Y based on X. Or we want to predict Y based on the variables X1 and X2, or instead of using addition, we can use multiplication, which means we don't want X1 and X2 to kind of act independently. We also want to have their interaction included in there. So this formula interface, this domain-specific language for describing how you expect responses are connected to predictors, can be extended in various ways. So in here, we're kind of thinking about, instead of using X directly, maybe a smooth function of X, or maybe we want to predict 2 Ys from 2 X's. And this also sort of illustrates what I mean by that a model is never going to tell you something you don't expect at some level, right? If this model is never going to tell you, hey, you've forgotten to add x2. That's actually a really important predictor. This model is never going to tell you, hey, x1 and x2 aren't actually linear. They've got some other smooth form. So the models really constrain what they're going to tell you about the data. So that's both a strength and a weakness. You have to be aware of that. You have to know that the model's not going to tell you. What it can tell you about the data is fundamentally constrained. Okay. So we're going to talk a little bit more later about the domain-specific language I developed for visualization, ggplot2. But the basic idea is a visualization is a mapping between data set and things that we can perceive. So the basic idea of ggplot, we give it a data frame, we say how we want to connect, so AES is short for aesthetics, how we want to map the data to aesthetics, things that we can perceive. So here we're saying we want the X position to be given by variable 1, the Y position by variable 2, and then the color by variable 3. And then we need to specify how we're going to represent each observation. So in this case, we're going to use points to create a scatter plot. And then we're going to add on a layer, which is a smooth curve. So not only do we want to plot raw data, typically we often want to plot some statistical transformation of the data. We want to plot some model that predicts Y based on X, a smooth form of X, and see what's going on. So I'll talk about this in much more detail shortly. Transforming, so when we're thinking about transforming data, I'm not just thinking about the kind of the classical statistical transformation where we might, log one variable or square root one or arcsine square root another. What I'm thinking about is generally how do we kind of aggregate our data, how do we rearrange it, how do we reshape it to get it into the form that's most suitable for analysis. So typically you need to do this step because when you get your data, it's not in the right form for you to feed to your modeling and visualization tools. And I mean, my experience working with data from all sorts of people is it's just absolutely astounding how creative people are with the way that they store their data. And a huge part of any real data analysis is just getting the data out of whatever crazy format they've stored it in into something standardized, something useful that you can work with. And I have a few examples of that coming up. But so I think there's kind of 4 key verbs associated with transforming your data. So subsetting or filtering, mutating or transforming, where you're adding on new columns that are functions of the existing columns, arranging or reordering. So typically, just changing the order of the rows doesn't make much difference to the modeling, but it's pretty useful when you're looking at the data yourself. And then finally, summarizing, where you're condensing multiple values down into a smaller number of values. So those are all useful by themselves, but really they need to be combined with some kind of group by operator. So I want to say summarize by treatment group or transform by patient. So we need some kind of combination of these basic verbs with a group by operator. And then we need a few other things. When we're working with multiple data sets, we need some way of combining them together, like an SQL type join, or maybe sometimes we just need to match them up. So we want observations in data frame A that in some way are included in data frame B. So we'll see some more examples of these shortly. Okay. So what I wanted to finish with, to kind of try and make this as concrete as possible, is show how I've used all of these tools in a data analysis. And I've just been exploring this interesting data I've got. So it's every single death that occurred in Mexico in 2008, and it's at the individual death level. So I've been interested in data like this for a long time. There's all sorts of interesting relationships between like temperature and deaths from heart disease and so on. But unfortunately, in the US, you can't get any data on this because Americans are very concerned with data privacy. It seems so far that Mexican government statisticians are not so concerned. So if you want to get this data for the US, you can fly to the CDC and you can work on it in their computer lab, and you're not allowed to bring anything out of that isn't approved by them. And in Mexico, they just put it all on the web, so it's a little bit easier to analyze. So there's a whole lot of variables in this data set. I'm going to look at 3. So COD, the cause of death, HOD, the hour of death, DOD, the date of death, and then the location where they died. And what I'm going to try and focus on in this analysis is to look at how do those DSLs help us understand this data. So we'll start by looking at cause of death. So here's a fairly simple plot. So on the x-axis, I've got the number of deaths on a log scale, and on the y-axis, I've got the cause of death. So just a very, very high-level summary. One thing that I think is kind of interesting about this data is the 11th highest cause of death. So when I saw this, I thought that was pretty surprised, right? To me, that seems much, much higher than I would expect homicide to be in this ranking. But does anyone know what the 11th highest cause of death in the US is? Suicide. So I'm not entirely sure what's better. So in Mexico, people are killing other people, and in America, they're killing themselves, I guess. So neither of that's particularly appealing. But let's see how we got to this plot. So first of all, so this is some R code. So how many of you have seen R code before? Okay, so even if you haven't, it's similar enough to any kind of algol derivative, I guess, that you should be able to see what's going on, and I'll kind of point out the important functions, the important things that we're doing. So I'm going to start by loading ggplot2 and plier packages. So ggplot2, the DSL for visualization, and plier, the DSL for data transformation. So one note going back to the prickliness of R help. So you use the library function to use R packages. And should you ever refer to an R package as an R library or an R help, someone will very indignantly tell you that you're a moron and you're using the wrong word. Somewhat ignoring the natural confusion here. Anyway, we're going to load those packages, load up the data, which I've just stored as a binary R data format, just because loading in a big CSV file, this is a little bit quicker than loading in the CSV file. And then I'm going to do some analysis. I'm going to start by counting the deaths broken down by cause of death. So this is going to give me a new column, a new table. In one column, I've got the cause of death, and the other column, I've got the number of deaths, the frequency of deaths. And then I'm going to arrange that in order of descending frequency, just so I've got it nicely. When I look at it, I see it nicely ordered from the most common to the least common diseases. Then I'm going to join on another data frame, which I haven't talked about yet, but in this one, so COD is an ICD-9 abbreviation. It's like K17, which means they died of liver cancer. It's not very useful when we're looking at the data to have these opaque codes. So I'm just going to add on basically a lookup table that gives us a nice human-readable description of the disease. Next, I'm going to plot it. So the idea with ggplot, I'm setting up the relationship between stuff in my data and what I want to see. So I'm going to use the cause data set, which I just created. On the x-axis, right, I'm putting the frequency. On the y-axis, the disease. I'm going to display the data with a point, so each observation will be represented by a point. And then I'm going to modify the x-axis scale. So instead of a linear scale, I'm going to have a log 10 scale. So what I'm going to do in this presentation is kind of focus on the essence of the plot. So if you actually ran this code, you'd get a plot that was pretty similar, but not quite what I showed you. So to actually do the plot that I showed you, there's a little bit more work. I just actually looked at the top 20 causes, and I showed you the deaths divided by 10,000, and I'd reordered the diseases by their frequency and done a few other little bits and pieces. So what I want to show you here is the essence of what's going on with these DSLs. Whenever you're presenting data to anyone else, there's always a whole lot of fiddly little tweaking you need to do to make it understandable. So I think it's really useful to think about when you're doing graphics, the sort of the difference between an exploratory graphic, which is just for you. You understand what the variables are. You don't need fantastic labels. You're probably going to create hundreds of thousands of these. Most of them are going to end up in the trash. The complement of that is expository graphics. When you're trying to explain what's going on to someone else, you want to make sure your labels are correct, that you've got nice legends and so on. So I'm going to kind of show you the exploratory code, but the expository graphics. So I just kind of tweaked them to make it a little bit easier for you guys to see what's going on. Okay, so that was cause of death. I mean, again, if we go back to this, nothing sort of amazing. Most people are dying of heart attack and diabetes and pulmonary disease and liver disease and so on. So what I wanted to look at next in more detail is, well, when were people dying? And specifically, could we find diseases where people seem to have a different time course of death? So I'm going to start with a very similar plot as before. I'm just going to show you the overall what's going on by hour of day. So here we've got a line plot On the x-axis, the hour from 0 to 24. And then, again, on the y-axis, the frequency, so the number of deaths in each hour. So how did we create this? Well, so first of all, what can you see here? When do people die, by and large? Seems to be, by and large, during the day, right? There are maybe fewer deaths at night time than there are during the day. You know, you might wonder if this might be some kind of reporting bias that people only discover the bodies in the morning. Maybe that's the 6 a.m. spike when people wake up and discover the person next to them's dead. Okay, so how do we create that? Well, first of all, we need to do a little manipulation of the data. This is pretty common. Well, when I first did it, I discovered, hey, there was an hour of death, which was 99. You know, I know there aren't 99 hours in the day, so I figured out that this is probably actually a symbol for a missing value. So what I'm going to do is replace this with R's missing value, NA, which stands for not applicable. So one of the things that's really nice about R, maybe one of the things it does sort of make it a little bit more on the statistic DSL kind of languages is it has the support for missing values. So when we don't know what the value is, R is going to propagate that in any computation. So if you have a number you don't know what it is and you add on 4, you know, you still don't know what it is, and it supports this at a very low level. So I'm going to replace the 99s with a missing value. So if I take an average, it's not going to be skewed and so on. And then the other thing I'm going to do is I'm also going to, you know, there's only 1 minute at 2400 hours. That's 2400. So for the purpose of this, I'm just throwing that hour out. You know, it's a little bit lazy, but it's quick and dirty. So then I'm going to do the same thing again. I'm going to count up the deaths, this time by hour of day. Then I'm going to subset it to remove all the missings. I'm not interested in those. And then again, I'm going to plot it in a very similar way. Here's my data set, HOD. On the x-axis, I want the HOD variable. And on the y-axis, I want the frequency variable. And this time, I'm going to represent it with a line. So geom here, it's ggplot2 abbreviation for geometric object. That kind of determines like the type of plot. Is it points or lines or bars or polygons or so on? So if I put geom point here, I get the same thing, but I would just have points instead of lines. Okay, so then what I wanted to do is figure out, well, which diseases don't follow that overall pattern. So I'm going to show you here are the kind of 8 common causes of death that don't seem to follow that same pattern. We'll look at how I managed to find these, which shows a nice kind of cycle of a little bit of modeling, a little bit of visualization, a little bit of transforming, and then we'll look at some other ones. So what sort of causes of death do we have here? Any seem to break down into a couple of different groups. Kind of looks like we've got murders, right? So murders are interesting, right? You're more likely to get murdered at night than during the day. Got a couple of drowning ones, right? People drown in the afternoon. This one's sort of interesting, this exposure to electrocution, basically. People get electrocuted during the day. So it's reasonable, right? It's hard to electrocute yourself while you're asleep. And then we've got these basically traffic accidents, which you can see kind of peak. Or maybe there's some suggestion that they peak during rush hours. So how did I find those? So we've got, I forget, but there's about 10,000 causes of death. Right, so there's no way I can go through and look at 10,000 causes of death and pick out the plots that are interesting. What I need to do is come up with some way of modeling what do I mean by interesting, applying that to all of the causes of death, and then picking out the interesting ones. So there's quite a lot of code here. I'm not going to explain it all. I'm just going to kind of talk about the general idea. But basically what I'm going to do is come up with a distance metric between the overall time course and the time course for each individual day. So I'm going to do that by, first of all, counting up the deaths broken down by both cause and by hour. And here I'm going to use ggplot, which is my kind of by operator. So this is saying, take this data frame of frequencies, of counts, break it down by cause of death. Within each cause of death, I'm going to mutate it or transform it to add a new column, which is the proportion. So the proportion within a disease is just the frequency divided by the total frequency. Right? I want to try and get rid of that denominator, which is how many people died from that disease. Then I need to do the same thing for the overall, right, to get the frequency of the percentage of people dying in each hour over all diseases, and then I join them back together. So in one data frame, I've got both the proportion dying at each hour for each cause, and the kind of corresponding frequency over all diseases. So then what I'm going to do is, again, break it down by cause of death. This time I'm going to summarize it. So I'm summarizing each cause of death with two numbers. So the total number of people who died of that disease, and then this distance, which I'm basically looking at the average squared distance between the frequency for that disease at that hour and the overall frequency. So just kind of a quick way of picking out ones that are far away should have high values, ones that are close to the overall rate should have small values. So one thing I need to be aware of here, right, is this basic statistical idea that if you don't have much data, your estimates are going to be more variable. So I need to, when I'm looking at this distance or this deviation, I need to be aware of how many points we use to calculate it. So that's why I'm computing the n. And then I also decided, hey, if I've got any chance of picking up departures from the overall trend, I probably need at least 2 deaths per hour, right, at the minimum, right? If I've only got 48 people dying of a disease in a day, my ability to pick up departures from the overall trend is going to be very, very, very small. So what I did next is this plot where so each point represents a disease. On the x-axis, the number of people with that disease, and the y-axis with the distance. So what do you notice here? Yeah, right? We've got a huge amount of variation when n is small, much smaller variation when n is big. So one way I kind of drive this home when I'm teaching class is I do a plot. Like if you look at all of the basketball players in the NBA last year, you plot the number of baskets they shot and the proportion that they made, right? So it's pretty easy to think, hey, if I'm going to pick players for my NBA team, I'm going to pick the people who have the highest accuracy. The problem with that is, though, that you end up picking like 15 people who have 100% accuracy. But they're 100% accurate only because they made one shot and they succeeded in it. So whenever you're looking at any kind of statistical summary, you always need to be aware of, how much variation there is. So, I could do some kind of nice mathematical statistics and figure out what the theoretical properties are. I'm just doing something very crude. I'm also going to log transform it. So exactly the same plot, but now on a double log scale. And basically what I'm interested in are these guys, right, in this upper triangle. So these, for a given n, they have much higher values than average. So my kind of expectation is, that most diseases are going to follow that basically the same pattern. There are going to be a few that are unusual. I want to pick out those unusual ones. So this is a pretty kind of crude technique, but basically I'm going to chop off all of these guys here and examine them in more detail. So to do that, basically, it's hard to select a triangular region. It's kind of easier to subtract that line off. I'm using a robust linear model. I don't want my straight line affected by these guys up here, so I'm using a robust model which shouldn't be so affected by them. And then I'm just going to pick off the ones that have a fairly large residual, so they're more than some distance away from that line. I just kind of picked that with a little bit of trial and error and then divided that up. So then I'm going to pick out all of the diseases which are unusual by my characteristics, so a residual bigger than 0.5. And then I'm going to use basically select, go back to the original time courses, and then create those plots. So I split them up again, sort of just with a bit of trial and error, into ones that had more than 350 deaths and ones that had less than 350 deaths, basically because the scales are so different. They didn't work well on one plot. So these are the 5 diseases that had less than 350 deaths. So it's pretty small, right? That's 10, 12 deaths an hour. But I think I am picking up something legitimate here, right? So we see, bus crashes, lightning, drowning again, aircraft crashes, and SIDS. So even though these seem to be pretty small, these are these guys up here, right? Even though I've got a small n, I've got a much bigger deviation from the overall pattern than I might otherwise expect. Okay, so I want to conclude with my kind of main challenge from this, which was driven by this plot. So on the x-axis, I've got basically I've done the same thing we've done again and again and again. I'm just showing you for each day how many people died on that day. So we can see fewer people are dying in June and July, more are dying in December and January. So what's probably causing this? Probably weather, right? You might expect it's colder during the winter and more people die when it's cold. So this sort of led me on a mini odyssey to try and match up this deaths data to temperature data. So the first problem was to match up this deaths data to temperature data, I needed to figure out where each person died. So there's a location code in the field. The statistical department also supplies a database that gives the latitude and longitude for each of those location codes. So when I did that, this is just for each unique location, showing how many people died in that location. So do you see any problems with this plot? So we've got a few locations off the coast, right? So maybe, it seems a little unlikely that a whole lot of, like maybe 5,000 people capsized in a boat and all drowned here, right? We also see some sort of odd striations, right? So suggesting that there's something wrong with this location database. So one of the ongoing challenges with data analysis is matching up your data with data that helps you make sense of it, with contextual data. And in this case, my context, the location of each death, was wrong. But luckily, there was a different data set supplied by a different government agency. And when I used that to capture the latitudes and longitudes, I got this plot, which is a little bit easier to see if I just restricted to the locations which have more than 100 deaths. So how did I create this plot? This plot's interesting because it's got multiple layers of data on it. So again, I'm going to start off again by counting. I just want the number of deaths in each location, each combination of latitude and longitude. Then I'm going to have, so here I've got 2 layers on my plot. So my first layer is a layer of polygons. I'm using it from the states database, which basically has the outlines of all of the states of Mexico on it. Then I'm going to add on a layer of points, which comes from this locations data, and I'm going to map the size of each point to the number of deaths there. Need to do one little tweak to that size. We know that when we look at dots, we basically perceive their area rather than their radius. So I need to adjust the scale that's used to map values to radius. I need to do a square root transformation, which is what scale area does. And then finally, this is map data, points on a sphere. It isn't like the usual Cartesian coordinate system. We want to use a special coordinate system which uses map projection. So it doesn't really do much here in terms of, so the fact that we've got data over a sphere doesn't matter so much because we're on a fairly small region of the globe, just kind of flattening it out doesn't distort it too much. But using that coordinate system does ensure that we get the right aspect ratio, so that this does look like a map of Mexico. It doesn't look squashed or expanded in any way. Okay, so the next thing I needed, so now I've managed to locate the deaths. Next I needed to locate the weather station. So I'm going to truncate the largest part of this, which is, so I managed to find this data source that looked really promising, the Global Historical Climate Network, which has about 40 weather stations in Mexico. Unfortunately, it has the most bizarre data format you've ever seen, so it took me a while to pass that and figure out how to work with it and combine all the weather station data into one file, but we finally got there. And so this plot shows the locations of all the deaths that were within 50 kilometers of a weather station. So I guess I should say like 30 miles, but since we're in Mexico, And I'm from New Zealand. We'll go with kilometers. Again, just sort of a heuristic, right? That probably, I'm sort of sweeping a whole lot of stuff under the cover, right? I'm just kind of saying, well, I think the forecast from a weather station is going to be fairly reasonable for about 50 kilometers around that. There's all sorts of arguments you could apply to that, but this was a good first start. And then if we instead plot that, just showing the number of locations, the number of deaths by each of those weather stations, we can see there's one really big one, which is pretty close to Mexico City, but not actually in it. So Mexico City, I think, accounts for about 20% of the deaths. So there's about 100,000 deaths here all up. So I thought, well, let's just start for a single location. I'll just start with Mexico City. That's got a good number of deaths here. I'll match that up to the weather in Mexico City. So here's a plot of the climate data that I laboriously parsed and collected, showing the minimum and maximum temperature. So temperature on the the y-axis, the maximum in blue, the minimum in red, and the date on the x-axis. So can anything interesting about this plot? Yeah, there's some missing data, and in fact, 87% of the data is missing. So I just spent 2 days trying to parse this awful data format, only to discover out that when I finally get to it, 87% of the measurements are missing. So this was kind of a cause for great wailing and gnashing of teeth. But luckily, I managed to find another data set collected by yet another government agency just for Mexico City. I'll kind of skip the details of that. Yet again, more cleaning, more messing around with the data. So much of a data analysis is doing this, just getting the data in the right format so you can actually use it. But then I did get some interesting data. So each of these points now represents a day of the year. On the x-axis, I've got the minimum temperature, and on the y-axis, I've got the number of deaths on that day. So you can see it looks like there's some, I think we can kind of say, at least along here, that as it gets colder, more people seem to die. And we get maybe there's a little hint that also when it gets really hot, more people start to die. We can also look at the maximum temperature. So we don't see this relationship so strongly down here, kind of suggesting that it's the minimum temperature of the day, it's cold that's killing people, not hot, unless it gets really, really hot. Though kind of looking at this again made me doubt this data because so the maximum temperature in 2008 was 30 degrees Celsius, which is like 90 Fahrenheit or something, which seems like it's too... kind of would think Mexico City would be warmer than that, given that Houston's getting up to about 40 degrees from time to time. So I kind of, at every point in the data analysis, you kind of think, hey, what's gone wrong with my context? Is that really going to ruin my results? But the one plot that really was interesting to me is this plot. So here we've got wind speed on the x-axis and frequency of deaths on the y-axis. So I think this is pretty interesting because it seems to be showing as it gets windier, fewer people die. So this was a little bit puzzling to me, but then someone mentioned, hey, Mexico City has a lot of pollution. So it may be that on windy days, the pollution's getting blown away. On still days, it's kind of gathering and more people are dying from that. So again, this kind of raises more questions than answers. I also looked a little bit to see if I could pick out diseases that seem to have particularly strong relationship with the minimum temperature. None of these seem particularly compelling except maybe pneumonia, which, well, we kind of have some prior belief that pneumonia might get worse as it gets colder, but certainly it's hard to imagine why non-insulin dependent diabetes would have a relationship with weather, certainly directly. And a lot of these kind of upticks look like it's just 1 or 2 points that are making us think that curve is going upwards. So there doesn't seem to be much strength to kind of say individual diseases are particularly affected by the weather. Maybe if we had more data, maybe if I managed to find more weather stations across all of Mexico, I'd get more deaths and I'd have more power to kind of pick up those changes. I want to sort of conclude by showing the plots for that. the code I used for that plot. So again, we've got this daily data. It's got for each cause of death, the temperature and the proportion of people who died on that day. So temperature on the x-axis, proportion on the y-axis. Then I'm going to use points to display that data. I'm going to specify an alpha. I'm going to make the points transparent. So to deal a little bit with this overplotting problem, so I have some idea where the majority of the points lie. And then on top of that, I'm going to overlay a smooth. So just these smooth lines, which I've said this time I don't want any standard errors, and I want to make it thick. I want the size to be big so I can see it. And then finally this one, faceting, another really important component of the grammar. So typically of ggplot2, so typically we want to be able to recreate each plot for multiple subsets of the data. That's what faceting does. It says, I want this plot that has points and a smooth line for each disease. And the wrapping basically means here I've got a 1D ribbon. I'm going to wrap it around into 2 dimensions. There's also facet grid where you think about I want variables in the columns and another variable in the row. Okay, so that sort of hopefully that gave you a little bit of a flavor of how these domain-specific languages can help kind of express common data analysis tasks. So of course the big problem with this is that basically these domain-specific languages are designed by me and they're designed on the basis of the types of data analysis that I do. So one thing I'm really interested in is trying to figure out, am I basically an outlier or am I doing something common? So what are the kind of common tasks of data analysis? How can we figure out what they are? Then how can we figure out tools, both kind of computational and cognitive? How can we think about these problems better so that we're more efficient? And to do that, I hope to find out more about what other people are doing. So there's sort of some indication that it's not just me because people do download my packages and they do use them, but it's kind of it's hard to know what really are the common problems in data analysis. How can we develop tools to best solve them? So kind of overall, hopefully, well, I think you're probably already convinced about why you should use programming languages, but particularly for data analysis, it's reproducibility, automation, communication, and on the downside, it's got a learning curve. So R is pretty great. It's a bit slow. The community can be a bit prickly. It's sort of lacking a little bit of infrastructure, but these are all things that I think can be fixed and slowly in the process of being fixed. So one thing in the latest version of R has a bytecode compiler, which yields, nothing amazing, but for certain types of constructs, kind of 2 to 4 times speed up. So things are slowly getting better. And then finally, sort of what I'm most interested in is how can we figure out what the fundamental problems of data analysis are? How can we devise tools, domain-specific languages to make those as easy to solve as possible? That concludes my talk. I just wanted to quickly say that I'm hanging around Google until my meetup talk this evening. Val gave me that, which is a location, I believe. So I'm going to have office hours. So if you want to, stop by and talk to me, I'll be there 3 to 4 p.m. I'm really interested in hearing kind of, your, both success and failure stories for R. What are you trying to do when you do data analysis? Or, at any point, just feel free to send me an email, or I'm happy to chat about anything related to R. So, thank you. Uh-huh.
Nice to see New Zealand here. Interactions, a bit more creative content. Maybe I'll drop you an email about it, but I think it's like just you said, like 80% of the problems are in conditioning data typically. I guess I can see lots of ways to see like lookup tables to try and map outliers back into.
Yeah. Yeah, I'd be happy to talk about. I've been doing some other work recently, sort of thinking about tidy data. Or what format do you actually want for your data when you're doing data analysis? It's a really important challenge.
Yeah, just had a question about you mentioned 1 million observations being a limit you have there. So what are some of the issues that cause that then?
Yeah, so I'm sort of still, kind of personally trying to scale up the size of data that I work with. So, I mean, I try really hard in class. At least I've moved beyond like these 100 observation data sets. So, and I think it's I can get a class of undergrads on their own computers working with 50 to 100,000 observations, and that's easy enough to do in class. 1 million, I think, is achievable. There's all sorts of problems with my tools in terms of like ggplot2 being god-awfully slow, which is one thing I'll talk about this evening. So part of it, I think, is just sort of, there's like a programming challenge, right? My job, I'm not a software developer. My job as a assistant professor is to produce research and to new things, not make old things work really well. So there's sort of a tension in my life between how do I do kind of, how do I keep doing new things while making sure the things that people actually need to do, which we've known about for years and years and years, are possible. So I think just sort of in some ways investment onto the programming side. I don't think there's anything fundamentally wrong with R, which means it couldn't scale up. But I do think we do kind of need different tools for different scales of data that, I just don't see like this kind of interactive exploration. I'm not sure how well that scales up to like 10 billion observations when no matter how much computing power you have, it's still going to take, a couple of minutes to get a result back, and how that sort of affects this iterative cycle of transforming and modeling and visualizing. So I think that's an open question. Obviously I've sunk a lot of time into R, so I'm biased with that respect, but yeah, I think it's an interesting question. I'm doing a class in San Francisco on Wednesday and Thursday, but it's sold out. So, but I'm teaching the class. I've called it an R development master class. So one day is like advanced R programming, the other is developing R packages. So one thing that I'm trying to resolve personally is this kind of complete lack of material about how do you become a good R programmer. Or if you are a programmer in another language, how do you move to R? How do you understand kind of the things? I mean, there are a lot of things I did a kind of a traditional CS program. I learned Java, I learned a little bit of scheme and stuff, and then I come to R, and you just look at it and you think, this is crazy, this is ridiculous. How does it possibly work this way? So some of that is legitimate complaints that there is a lot of craziness in R, and some of it is just trying to understand that R looks at the world in a very, very different way from a lot more functional perspective than object-oriented, and just trying to figure out how can get people up to speed on that, writing kind of idiomatic R code that makes use of R's strengths rather than trying to force it to be like Java or C# or whatever. Thanks.